And again, these waves which propagate in the water, these giant tsunami literally means in Japanese harbor waves. Okay. Because they sort of, when they break on the coast, they rise up to a great height and submerge. Is what they do. So they are known as harbor waves. Tsunami means in Japanese harbor waves. Okay. So the height of the tsunami and all that can be estimated. So here, again, the propagation of the waves also. There are gravity waves and capillary waves. Any water, any body of water, say if I have a perturbation. Okay. Now, suppose I throw a pebble on a pond, I get ripples. Okay. So it's essentially these are capillary waves. Okay. The surface tension in the water that causes these surface waves to propagate. The deeper waves, suppose I got a bigger perturbation, I have an explosion underwater, okay, or some other thing, then gravity waves can propagate, okay, because the mass of the water, so they are buoyancy and so they can, there's a column of water denser than the surrounding thing, so that will be pushed. So this essentially has kind of gravity. Okay. So actually the formula for the frequency of the waves. So this depends on the wave number. So there's the inverse of the wavelength. And for gravity waves, we just have expertise as relation to the gravity. Omega square equal to GQ. Okay. And then since we also have capillary waves, the general formula for this is so the surface tension is also involved. Suppose gamma is the surface tension, and rho is the density of the liquid. So there's a K cube also. This is the general expression. So this is a combination of gravity waves and capillary waves. So you see now that what happens, there is a transition depending on the acceleration due to gravity, the density and the surface tension. There can be a transition from one to the other. Okay. So the gravity waves are the one, and the tsunami is nothing but a gravity wave, can propagate over long distances. And the velocity of the waves depends on the wave number. So actually the velocity goes something like v squared is gk. This is the general formula for the thing. Okay. So this is quite a the height of the wave. V squared is gh. Okay. H is the height of the wave. Okay. This is the height of the wave. So you can see now that waves which are at move high velocity are also submerged to a greater depth. Okay. Or you can use d for the depth of the wave. Okay. Depth to which it penetrates. Okay. That's d. So actually essentially is 1 over k. K is the wave number. Okay. Wavelength is lambda, so it's 1 over k. So you can see that the transition for some k, okay, or some corresponding to some wavelength, okay, depending on the density and the substitution. Okay. So actually you can see for what value the two will match. Okay. One will go into the other. Okay. So you can see from this that larger values of k, these capillary waves will dominate. Okay. And for longer wavelengths, okay, the gravity wave will dominate. Okay. So that's why the tsunami waves can be quite high. Okay. And they move at high velocities. Okay. And actually you can add this with the energy of the. For example, we read that the velocity achieved in the tsunami was something like 500 kilometers per hour, right? About a jet liner, or maybe 1,000 kilometers per hour. So how do you get such high? So the energy released probably in this quake is about 10 to the 20 joules. Okay. So at least part of this, quite a substantial part of this is transmitted to the water. Okay. Causing the wave motion. So you can roughly estimate the thing like this. We saw that area involved was something like something like 1,000 square kilometers. 1,000 kilometers into 1,000 kilometers. That was roughly the area involved. Okay. So roughly you have 1 million kilometers square. Okay. Roughly 1 million kilometers square. And so you can calculate roughly the kinetic energy involved. So you can so the depth is about you can say the depth of the thing was about say about 100 meters. Okay, that will be the roughly this was also reduced from the epicenter, where the earthquake took place. So they realized this much of the thing was this was the plate was broken off. Okay. The fault line, the length of the fault line and the area covered, they estimated that. So you can see how much volume this covers. Okay. How much volume this covers. So this was also roughly about 10 to the 18 cc. Okay. Cubic centimeters. Or you want the liters, 10 to the 15 liters. Okay. Or 10 to the 12 cubic meters. Okay. 29 cubic meters of water. Okay. So you know the mass of the water, and now you can work out the velocity involved. In this. So you roughly write and we square this roughly in the order of say 10 to the 20 joules. So we do this calculation, you get you will get a V of about close to what they said. Okay, 1,000 kilometers per hour. You will have to convert to second and all that. You can do this sum. Okay, so this gives an idea of how how these things operate. Okay, and of course for high values of K it will be a surface wave. Okay, small wavelengths, and the transition is interesting to work out. For example, if you know for water the surface tension to water is about 70 joules per centimeter, and density So we work out for water the transition wavelength or the transition frequency. It works out to a few hertz. Okay, about 12 hertz or something like that, 10 hertz. So that's roughly the. So for smaller frequencies or longer wavelengths, the gravity wave will dominate, and for smaller wavelengths and larger K, the capillary waves will dominate. Okay, so you can see the transition. So in this case clearly the surface waves are not important. Is the depth is the deeper gravity waves which are important. So your dk is important. So you can estimate the velocity of the waves in this fashion. Okay. So this is one way, and you can calculate the potential and how much is heaped up. Imagine so much of water being heaped up. You can calculate the potential. So that also matches with this. And just to give you a rough idea of the numbers involved. And suppose if you have a different planet like Titan, for example, Titan is supposed to have oceans of liquid methane. Okay. Suppose now a similar thing happens there. You can calculate for that particular fluid what is the surface tension. See, inside water, suppose you have alcohol, the surface tension is much lower. Okay, it's around 20. Whereas the density is also comparable, 0.8. Okay. So again, the crossover frequency one can work out. So if you know that the particular planet is covered with oceans of some methane or whatever, or ammonia or whatever, you can again do okay. And of course it depends on G. So suppose you have got one of the findings of the Cassini spacecraft is Titan has got weather similar to the Earth, but running on the methane cycle, liquid methane cycle. Probably some nitrogen is also there, liquid nitrogen. So since the surface gravity on Titan is quite small compared to the Earth, okay. Again, the frequency of the waves, everything will be affected, okay. Or given a wave of particular frequency, the velocity will be different, smaller, okay, velocity will be smaller, propagation times will be longer. Or if you take another example, Europa is one of the satellites of Jupiter, they think there may be a lot of water below the surface, okay. That's why some spacecraft are thinking of launching to exclusively monitor the satellite Europa, okay. So suppose this has also got a huge liquid ocean underneath, below the surface. So it will be subject to all these kind of wave phenomena. Okay, but the surface gravity in Europa is only 1/7 of the Earth. So you see any velocity of any of these waves will be much less. Okay, so it's easy to deduce many things from all these things. So it all follows from. So I gave you some idea of how they estimate for earthquakes. Okay, this energy. Okay. So next time you read some earthquake was there, Richter 7 or 9 or whatever. You can plug in the formula and you can see how much energy is released. Okay. And since the logarithmic scale, Richter 1 will correspond to hardly 20 joules. Okay. In fact, if I drop this duster on the floor, that's about Richter 1. It's to create a ton of Richter 1. It's a logarithmic scale. So it's like the magnitudes. So So magnitude 30 doesn't seem very different from magnitude 1, but that's the limit of the Hubble telescope. So it is a trillion times fainter than 40 volt. Okay. So that's about Richter 1 things.